Yeah.
Gravity. And then rope. Oh, and then mu. Oh, actually,
I mean, F friction, right?
yeah.
Yeah. Yeah. Is that all the forces?
That one like the force rope.
There's also pulled. Yeah, there's a rope tension. Yeah. So for question B, you want to find a normal force. And I said it in the beginning when we learned like a normal force. Not the beginning. Actually, the end is probably making sense. Normal force don't really have a formula. And it's not always equal to mg. But it's normally always done by Newton's first law. Because in this direction, it's not moving, right? You can move horizontally, but in this direction, it's not moving, right? Is it moving? It's not moving, right? So Newton's first law always applies here. Does that make sense? Which means F Newton, F like normal, and gravity. Let's see, gravity is a little bit bigger. And is there anything else? Is it going to be balanced?
No.
If there's only two forces, they are balanced, right? Because it's not moving, right? Newton's first law is working.
Yeah.
But there is something else. What's?
Oh, the rope.
Yeah, the rope has a component, right? This one is gonna be have a triangle law. Right, this is the theta, this is ft. So I can find this. Can I find this? I can find this, right? I can find this. If this is ft, oh, we can always draw another diagram to make, well, let us see better. But this is ft, this is theta. So I can find this ftx or y, right? Vertical. And which is going to be some little for fty in here. As long as I can find fty, I can make a big equation, let them balance, right? Does that make sense? Can you find fty? Not in here. Don't find fty in. Find fty in here. Let me draw a better one. Better one is this. See, I'm gonna make component, right? So this is the total for. I'm gonna make two components, making it normally always horizontal and vertical, not always, but normally it's the perpendicular one that I like to use, right? Does that make sense? This is ft. This is theta. I want to find fty.
Oh,
Right?
sine theta.
This is we say that the also this Princeton book also said it. It's always make the components in x direction and y direction, right? That'll be easier for calculation. Yeah. Fty is So since I have FTY, and then can I find the normal force then? You have this one and this one add together, which is gonna be UMG. Saying this is FTY and this is F normal. Can you make an equation for this? Newton's first law? F net is 0, right?
Fm equals m minus fty.
Yeah. Mm.
So, oh, okay. So then it would be, if it
Yeah.
was only in terms of that, it'd be G minus ft sine. Wait, so
This is B, right?
mm,
We're using FT, using theta, using G, and using M, right? So
yeah,
this is right.
no,
And then also question C2.
yeah,
Sure, let's do C.
C2.
How to find C then? I think you probably know a little.
Compute the acceleration of the create. So the force of the friction. Ft equals. So the force net equal to.
Whether you can draw a new diagram. Draw a lot of them. Do you like comic books?
Yeah, a little.
Yes, it's a little bit like comic book. Just write a lot of different for the special case. Draw a lot of diagram to indicate one thing.
So you're pulling it this way. Is Ft. You also have the friction. The total force. So F total.
You mean F net, right?
F net, yeah.
Same thing. Yeah. I read that total sometimes. Sigma. Oh,
Equals Ft minus F friction.
yeah, minus friction.
And then
When you say FT, do you mean FT in here?
yeah.
Technically, this is not exactly F net. This is F net horizontal.
Oh, F net X.
Yeah, so this is FTX, right? FTX. Sure. Now, what's FTX then?
FTX is the horizontal component. So it's
Yeah, so we can draw this one
mg
again.
cosine x
Yes,
mg
and
cosine mg cosine theta.
technically it's not mg because what you draw
Oh,
is
it's not
this is
mg.
ft. This
ft
is
ft
theta.
cosine ft
Yeah,
cosine.
ft. Yeah, that's why I said draw a lot of diagrams. Otherwise, we'll keep forgetting about this.
ft cosine theta.
Yes, so this one is okay. You already have this.
Then F friction is mu times the normal force, which is we found before. So it's
Yeah,
FT.
mg minus that ft fty. Yes, which is ft times sine theta.
Then you divide by m to get the acceleration.
So this one, f p cos theta minus this mu mg minus ft sine theta, entire thing divided by m, right? Does that make sense? Although it's complicated, but I'm asking what they asked, right? They're not giving me data. So is it making sense now? That's also a reason I said normal force doesn't really have a formula. You have to draw the diagram. Normally use, well, regularly we use Newton's first law as an equation, balanced equation. Yeah, and always, not always, a lot of time it relates to friction. Question 2? Every question is a little difficult. Including last chapter, previous chapter's free response also a little difficult too. You have to make sure your deducing is right, because also the previous chapters like free response questions, some of them really showed up in the real test, so you really have to do it step by step. Several times.
E2.
E2. So respectively, on a flat frictionless and a force F is posed on block 2, and M1 and M2 massless string E2. If the string connecting the blocks were not massless, but instead has a mass of M, determine the acceleration in terms of this. And the second one is the difference between the strength of the force that are connecting the string exerts on block 2 and the strength of the force that connecting the string exerts on block 1. Please state the answer. Okay. Well, this time they have a mass, which means 3 objects now, right? So there is a little mass in here, right? So find acceleration. What's the acceleration for the first one? I will use this.
F equals so A equals F over M. Force here, it's
F?
just a big F. Just a big F.
Yeah, and mass?
M1 plus M2.
Yeah, so yeah. As long as I have this acceleration, I can focus one. First one, he want to find the difference of the two force. Well, I can find each one of them, right? Now block 2. Let's say in that order. Let's do block 2. Let's focus on block 2 only. If I focus on block 2 only, so my force, my diagram for block 2 is a force F in here, right? I must have a tension from this string, let's say this Ft. And what else do I have? It's probably only 2 force that I have, right?
Yeah, yeah, gravity and normal force cancel out. So
yeah, that one balances, so I'm not thinking about the vertically. I actually do it in the beginning, but now I know, just I don't want to. This one is probably a little bit longer, so that's why I go in that direction. So this one is balanced a little bit. So now I can use my f minus t1 equals to m2a, right? Does that make sense?
Mm-hmm.
Which
F
means, yeah,
minus
f minus t1, right?
Oh,
Yeah.
oh yeah, okay.
So
Okay.
t1 is, according to this, let me just get t1 directly. T1 is f minus m2a, right?
Mm-hmm.
I probably learned from your method. Let me write this f minus m2 time, I'm going to write a all the time and then and substitute a in the end because a is easier. And then in the same spirit, I can do this is from situation 1 for block 2. This is for situation 2 for block 1. I'm thinking about a block 1, so he has a tension in here, right?
Mm-hmm.
T2, right? T2 is probably the only force horizontally for him, right? And this also balanced, right?
Mm-hmm.
So I'm going to write T2
Equal
equals
to
to
M1A.
M1A, right?
Uh-huh.
So, and he's asking for T2 minus
Minus
T2 minus
T1.
T1 or T1 minus T2. Which one is higher though? Well, probably not.
Difference between the strength of the force of the connecting
Probably
string.
the
T1 minus T2.
yeah, I think probably T2 is a little bit less. So let me use T1 minus T2. It doesn't really matter for this question actually. T1 minus T2. Because I can compare who is
Substitute.
bigger in the end. So T1 minus T2, which is F minus M2A minus M1A, right? Does that make sense?
Uh-huh.
So then it's just F minus, I think A I can get it out and by M1 plus M2, right?
Mm-hmm.
Since A, you already find it in this question, I'm going to use F minus F over M plus M1 plus M2 times M1 plus M2. So I think I get F out, so it's 1 minus that, complicated fraction, and then F become M plus M1 plus M2, and then I think it's M plus M1 plus M2 minus M1 minus M2, which is eventually going to be MF over all this. Does that mean? Is this making sense?
Mm-hmm.
What stopped you before for this too? Complicated a little?
Uh, yeah, and I just didn't really know what was asking me.
It's I think every step you're okay, right? It's just a little long for this.
Yeah, I just think like in total it's just confusing.
So which is that's why I said total and then system is required to know. Well, actually system you don't really have to know. All this question that can be done by separate method. Separate object method eventually can deduce, logically to the system one. So system method is not required, but separate object method is required. Does that make sense? So
Yeah.
we just do it separately and then you will know.
Number 3 is uh number 3A I just can uh figure out.
Number 3 is okay.
No,
Number
I
3
can
also
figure
is,
out 3A.
oh, number 3 is difficult because it combines two.
Yeah.
Starting with A.
Yeah.
In this figure, assume Paul is frictionless and massless. The surface, if the surface, the inclined planes, it's theta and M1 and M2. Determine what the value of theta will cause the box to accelerate. And then the second situation to slide up the rim at a constant speed. If it is accelerate, let's say first one is accelerate, then which means we probably need the force diagram anyway, right? Free body diagram. Let's see what is the forces that I have. And also this one is probably for like a separate one because, well, you can imagine the system, but still we have to find acceleration. So this one is the normal force, right? There's a gravity and there is what else do I have? Tension? Do I have tension? A little tension probably. Strain probably have give us tension. And friction? No, because it's frictionless, right? Good. So if that's the case, that's my diagram 1. But remember that the textbook, Princeton textbook says the second one that I said, draw the components in the right appropriate XY system, right? Because this one is complicated because there's several directions not in XY system. We don't like it, right? Does that make sense? And also because you also learn that like the gravity always divide into this too, right? The mg sine theta, mg cos theta, right? Do you remember that? So that is also another hint. So that's why we like for slope question we always like this parallel with the slope direction and also perpendicular to the slope direction. So I'm going to deduce that. I'm going to divide that into these two components. So I'm going to write a different one, which is kind of like this. This one, and also there's a one like this, and there's a one like this. Right, and there's a tension like this. Does that make sense? I'm going to not using gravity anymore, but I'm going to use the mg. This one. This is what? Do you remember? This component and this component?
Oh, mg in
mg sine.
mg cos.
You can deduce or you can remember. We deduced last time.
Yeah.
This is mg sine, this is mg cos theta, right?
Oh,
Instead
yeah.
Instead of that, the other one, I'm going to use this. So it's better to remember this. So automatically, this is mg cos theta. Is this direction balanced?
No.
Wait, if I move this along the slope upward, but in this direction, perpendicular direction, isn't that always the same? So which means perpendicular to the slope, no displacement, no velocity, right? You moving in here. That's why we like XY system. You move in one direction, but in the other direction, we normally don't move at all, right?
Yeah.
So which means it's at rest in this direction. So that's why they balanced. Newton's first law is going to be applied in one direction. Actually, last time we learned Newton's like a first law and second law and third law. They can always work what? They can always work in the separate direction. Does that make sense? So in this direction, I can just, apply the Newton's first law and forget about others for a second. So this one is going to tell me F normal is going to be what? mg cos theta. That makes sense? And this one is mg sine theta, and this one is F tension, right? So if this one balanced, what about in this direction? Is this direction balanced, or ft higher, or mg sine theta higher? I'm drawing this one better because I hope it goes up, right?
Yeah.
So let's return to if the surface, they said, what theta will cause the block of mass 1 accelerate up? Which means your ft want to be higher or lower?
FT to be higher.
Ft be higher, right?
Higher than mg sine
Yeah,
theta.
so that's the
Oh, for
ft,
accelerate?
yes, higher than mg sine theta. Does that make sense?
Yeah.
Mm. But then again, what's
and then
ft?
for
Hmm?
FT is it? Oh, is FT
Is ft known?
it's
We don't
wait,
know
yeah.
ft. We have to find it actually.
It is gravity.
Yeah, there's a way to find ft, right?
Is it just M2G?
Yeah.
Is that FT?
Oh, I'm 2GST. Oh, not exactly. Do you remember we learned a question about this in here? They have a pulley and there's M, right? There's MG. This
Oh,
MG,
you need
right?
to subtract
Yeah, I need to find the
normal.
tension. Do you remember they have several follow-up questions? Eventually they find the tension, right? So the tension is not exactly mg. And also the tension can't be mg. See, if this tension and mg, if they are balanced, say they are
Oh, the
balanced,
balance.
you can't move then, right?
Mm-hmm.
But you have acceleration, though it's better to move, right? So that t, you have to calculate yourself. It's not exactly assumption that the t is mg. And also it's against the other one. So it's definitely not mg. So how do we find that tension? We have to use something that we learned before to find that tension.
The the gravity.
Let's forget about this. This is why I said it's like a comic books. You have to forget about this, like turn the other page for the comic books. So I have to draw again. This time I'm not focusing on this one. This time I'm focusing. This is the comic books is sometimes for one scene they read several. And now I can focus on one part, which means kind of like that one, right? Remember? So I'm gonna use the system method now because that's kind of easier. Does that make sense?
Mm-hmm.
Yeah, the kind of easier is because the force is gonna be m2g and m1g, right? I mean the gravity, but that one can be transformed into m1g sine theta. Does that make sense?
Yeah.
Yeah,
Oh, so it's
because
M2G minus MG sine
yeah,
theta.
yeah. So that's m2g minus your preventing force is only m1g sine theta is the preventing force. This is the driving force, right? This together is the F net and divided by the entire system mass, which is this, right?
That's the force. Yeah.
Yes.
Yeah. Okay.
Mm.
Wait, so this is total.
This is
This
an
is after that.
acceleration.
Oh, this is okay.
Mm. Which means I want my acceleration,
To be 0.
yeah, to be
Okay.
greater than 0. So I can, well, then I don't really have to use the other one. I can just use this one, greater than 0, and this will be accelerate up the ramp, right?
And then slide up the ramp at constant speed would make it equal to 0.
Yeah. Yeah, it's kind of easier in that case.
Okay.
Is that making sense?
Yeah. Let me see.
Which means m2g minus m1g, it's sine theta, right?
Yeah.
G, if this is greater than 0, then g is out. I can simplify g divided by g on both sides of the equation. Then that'll be m2 greater than m1 sine theta, right? And sine theta is less than m2 over m1, right?
Mm-hmm.
That making sense?
Mm.
Let me see what A asks. If the surface of the incline determine the value of C, that will cause M1 to etc. Okay, this will definitely. So I can use inverse function, right? Are you familiar with inverse function still?
Uh,
Are you familiar with this? Inverse function?
yeah. Yeah.
Yeah. Oh, they didn't give us the data, but if I substitute, I can get an x of theta. For example, let's say theta is 37.5 degree, right? This is a requirement, right? For this first thing to happen, right? So theta is less than that. Is this one okay?
Mm-hmm.
Using the system is probably better. Or using a separate one that still have the same result. And second one, slide up the RAM at a constant speed. That's what. Let me get back a little bit. When they slide over the RAM at constant speed, not a greater than 0 this time. And this is our A, right?
Yeah.
The second one is what?
Theta equal to
Equal to 0, right? That one is greater than 0. This one is equal to 0. And basically, it's theta equals to sine -1 m2 over m1, right?
Mm-hmm.
Does it make sense? And so what we do for A before is gonna be helping us with B. You're not doing B either, right?
Yeah.
Yeah, so if the coefficient of the kinetic force, kinetic friction between the surface of the incline and m1 is mu k, and derive, but not solve, an equation. Oh, it's a derive an equation, that's good. Satisfied by the value of theta, which will cause the m1 to slide up term at a constant speed.
So constant speed. Control constant box. Slide up. So acceleration 0. Vision. UK. Derive but do not solve the equation satisfied by the value of theta. What's wrong?
You basically want us to find a big equation.
Yeah.
With mu k and theta. And of course, what I did provided is with the M2, M1.
Follow F net
Constant speed is a key too.
equals MA. F net. So we just need to find F net. So then we have FT. Right? Where did I get that? G sine theta. Then we also have friction. Friction adds on to this, right? Kinetic friction, so that's UK K times mg cos of theta. Yeah. What theta is that equal? Okay. So we subtract the all.
Yeah.
So FT minus G sine theta minus mg cos of theta over m equals 0.
Oh wait. Mu mg cos theta.
Oh, I
It's
forgot.
the
Yeah.
same. It's the same because the because technically you don't know ft, right?
Yeah.
You don't know ft, so it's better not into making a fraction form. Let's just make if we don't really know it's going somewhere, it's better to write, is it m1 or m2? M1. It's gonna be M1A, right? Let's just leave it there. Why I don't want to, because ft, if we know ft, we can write it like that. This is equation, one of the equation, right? Because this one, you see, when they write, they don't want ft in here, see? So this is half of that. It's, you can write another one. So this is, you're using like a separate object method, right?
Yeah.
So now this is one object. What about the other object?
Oh, I have to find that.
Yeah, otherwise we can't really get rid of ft.
So FT equals to M2G minus mg sine theta.
No, that one, I think that you had, that one is actually the entire system. You want to use the system, or you
Oh,
want to use the other,
just
just
okay.
M2,
I see.
because you are using. It's better
Okay,
to
yeah,
use one method first. If it's really not working, we can use both methods. So we should talk about M2 directly, not talk about the system, because you're using one object. It's only natural that we talk about the other object. So this one, also you can draw the diagram, right?
Yeah.
It's probably this one higher. This is M2G, and this is FT, right? So can you write an equation like this one too? Not that one. That one you wrote is the system. Actually, that system, if it's m2g minus, is the entire fnet we wrote is like that. But this one is not like that.
Hmm.
Also Newton's second law. This is Newton's second law number 1. Also Newton's second law number 2. What's the fnet now? For m2, of course, for m2, not for the
Fnet
system.
equals mass times acceleration. So ft equals. Fine.
So the fnet is going to be m2g. I only have 2 force, right?
Yeah.
m2g minus ft, right?
Yeah.
And still equals to my m2a, right? Because 2 acceleration on the same string, they're supposed to be the same, right?
Yeah.
At least in this situation, we say it's the same. Same velocity, same time, same acceleration.
Oh, so then just ft equals.
Yeah, so now I don't have to find ft because they don't want ft. So that's why they said they don't want to derive, they just want to divide an equation. We already have an equation. It's the sad thing we have ft, they don't want it. They can get rid of ft, use elimination, right?
Yeah, you add them.
Add them, yeah. So then it's just f2 m2g minus this m1g sine theta minus mu m1g cos theta equals to m1 plus m2 a, right? And also this is constant speed. What does that tell us?
Oh, equals 0.
Yeah, so this is 0. So if you equals this one 0, it's also working.
Oh, so then the a in both would be 0.
Yeah, so this is
And
0.
I cancel it out, so it's just 0.
Yeah, I can get rid of all the g then, right? I have a lot of g. So basically it's m2 minus m1 sine theta minus mu m1 cos theta. That's 0, right? That make sense?
Mm-hmm.
Yeah, this would be the equation, right?
Mm-hmm.
So what should we be careful? We should be careful with, sometimes we use system, sometimes we use the separate object, right?
Mm-hmm.
Now you can know that separate object is actually more popular, right? They're more popular. Does that make sense?
Mm-hmm.
Yeah, a lot of
Yeah.
them, yeah. And also it's more complicated, but they're more popular. This one you can also think like as the system. Yeah, but system sometimes is difficult to imagine. So use if you really get the system, you can use system. Otherwise, using the separate object is well, is required at least. Question 4. Let me ask you something. The one that's, well, it's the free response in chapter. This question you did step by step, right? If you still
Which
have
one?
the records, you can send it to me because this question also is tricky. Not like the Turing question.
Which one?
Did you finish this on some paper?
That one?
Yeah. You
Not
can do it if you
entirely.
haven't. If you don't really have the record, you can just do it, and you can send to me. I can check for you because they require a lot of steps too.
Okay.
which is the previous chapter. Free response, especially free response.
Okay.
Question 4.
I did question.
Question 4 is okay?
Let me check. I think it was it. I think it was.
Did you check with the answer sheet?
Yeah, I did.
Okay then.
Yeah. Question four is fun.
Okay then. Then we can go. Oh, and also for the new one, that we also have to learn circular motion, which but it's well for later. We can save it there. It's not much difference. We can
Okay.
just follow this order. Have you learned work before?
Uh, a l- a little.
So what do you know about work? FD?
Uh, no, I did like potential and kinetic energy before.
Oh,
Actually, yeah.
okay.
One half mv squared and
Oh, yes.
I had mass times right.
Yeah. And this is the formula, and the phenomenon normal one is this. There is force pushing this F, and after a little while, it goes the distance d. So you can see the effect of this force. Of course, if we talk about a frictionless, and so the effect of that is the force making a distance d effect, right?
Mm-hmm.
Yeah, that's why we say the force done the work. So that's why we have this. I mean, it's making a little sense, right? Work is F time distance. Does that make sense? But if
Mm-hmm.
you can't really make, if you really can't make this move, you say no work, right? And now it's a little work. What work? F time D work. The effect is D, but well, force is involved. Force is the reason. So this is the formula. And the units is actually Joule, which J is the unit of energy, right?
Mm-hmm.
Energy is kind of like work. Have you learned that?
Energy.
Yeah.
Yeah.
For example, we can say if this is a chocolate bar, so you're eating this, which is energy, right? But after
Yeah.
eating this, don't you can do some work, moving some, big case. Does that make sense? So somehow the
Uh-huh.
energy is transformed from the food to you and then do the work. So somehow I can say that kind of can be transformed from one form to the other, right?
Mm-hmm.
So that's why it's, of course, if it's transformed from one form to the other form, then it's the same J, same unit. Example 1.
And you slowly lift up the distance of 3 meters. How much work did you do to on the book? Work equals source over distance. Oh, so we have to calculate the form.
Yeah.
Lift up just 2 kg. You lift it. Constant velocity. Well, constant velocity, that means there's no acceleration. So
Yeah.
the force is just 2. So 2 times 3 is 6.
Hey, the mass is 2.
6 for
The force is what?
2.
Wait, the mass is 2.
The mass is 2.
What about you need the weight, right?
Oh,
Yeah, we need the force of the weight.
wait. So
2 times 10.
that's from this.
Yeah. I need a force, right? I need a 20, right?
Yeah,
20
so
newton.
oh, it's 60 then. 60 then.
Yeah. So this is the work that I have done. Means I'm moving that there is a effect.
60 joules.
60J. And also, do you think work is vector or scalar? Does work have direction, basically?
Work. Yeah.
Well, on some level, it does feel like that. For example, if I'm standing here, I can push in that direction, doing like 100J work. I can do in this direction. I can do this direction 100. I can do this 300, 100J, right? See, that all 100J. Does that make sense? So they don't have a direction. Does that make sense?
Mm-hmm.
So work is a scalar. Sometimes they do ask in the real test, but which concept, which is scalar or like a vector. So work is not. And also you can also think about the energy. I said energy and work can be transformed. Energy and work can be transformed. Of course, energy doesn't really have a direction, right? You can't really say a chocolate bar have a direction. Right?
Yeah.
Yeah. In that spirit, I say work doesn't really have direction. You can
Wait, so
say
is work and energy the same?
they can be transformed, not exactly the same.
Oh, so energy is stored work.
Yes. Oh, yeah,
Okay.
kind of. Yes.
Okay. You can use energy to do work.
Yeah, I can use energy and make it
Okay.
do work, right?
Okay.
Or I can make work and transform into a kind of energy, I mean, on some level.
Okay.
Yeah.
Okay.
And
Yeah.
some
Okay.
people say they do have a point. They say, can I call this one, for example, the same person? Can I call this 100J work to the left? And this is 100J to the right. You can say that. And I can also say that this is a north direction, like a 100J. You can say that, but that's just a little messy. Does that make sense? I don't want to know direction. You can specifically say something, like which direction. It does have a direction in that. But in work that we have, we don't have a direction. Does that make sense?
Yeah.
You are, well, you're basically saying that it's a good point. They can have a direction, but the one that we like it is they don't have a direction. And they can describe more. Although your like a left 100J is more specific, but it describes less things. And also, especially when the conservation of energy happens, it doesn't really help a lot in there.
Yeah.
So we can go on. So it's a scalar, and sometimes, yeah. For example, sometimes we do have 100J work and negative 100J work. It does not mean direction. It just one is kind of like driving, one is kind of like a preventing. That makes sense? Yeah, for example, if I push this thing around, this is the force that I gave. It's called driving force, right? It's driving the one that's, make a move. And the other friction is like preventing force, right? So this is more like we say this is positive and this is negative. Does that make sense? But it does not indicate a lot of direction in there. It's just one is driving work, the other one is preventing work. Does that make sense? And the example is just like your motor. The motor for the motorcycle is always doing driving work, right? But the friction normally always do the like a preventing work, right? So I can say one is positive, the other is negative, right? Work at angles. If I do, let's just say, if I do it like this, what's the work done? I give it a force F, I make a distance D, and I have angle theta. What's the work?
angle theta. What's the force times distance? Oh, but the force is so if it's this way.
So in the direction of my distance, yeah,
Cosine theta.
yeah.
Times
You can find the component, right? F cosine theta, right?
yeah.
Or you can say fx over f is cosine theta. So fx is f cosine theta. Basically, I'm saying that my force only have a f cosine theta, which actually does the right kind of work. Does that make sense?
Mm-hmm.
And which indicates the other component is not doing any work at all. Is that make sense?
Mm-hmm.
Only the component from the force in the direction of my distance. That is the real component who does the work. Does that make sense? Which means this one doesn't really do anything. See? Because you are still here, right? You're not going up against you're not going away from the brain or going into the brain. So that's why we have this. Some textbook describe it as the work in the direction of the distance, or force in the direction of the distance. This is the force, in the direction of the distance. Or some textbook describe it in the like a distance in the direction of the force, also making sense. Let's just remember this one. That'll be okay. Oh, and they have this, but we can deduce by ourselves. Cot theta, as long as this one is easy to understand, right? Between 0 and 90 degrees. So this until 90.
And then
when it's 90, it's a little difficult to understand. 90 is more like forces in here, and then your distance is in here. They say it's 0. According to trigonometry, it's working, right? See, because cos 90 degree is 0. Does that make sense?
So is this only a horizontal axis?
Yes.
Oh, okay.
Which means there is no work at all at this moment. I mean, in this process.
Yeah, okay.
Does that make sense?
Yeah, and then okay, yeah, makes sense.
Yeah. And also because they make a very small like a component. You see, the higher you get, very small component, right?
Smaller. Yeah.
Until you're so small, it's actually 0.
Yeah, makes
And
sense.
this one is constant speed, and this one is increasing the speed, of course, because you make a little acceleration in there or a little work in here, right? So that's why the speed is increasing. Does that make sense? And also, if this happens, which means it's more like this, but your block is going in that direction, your velocity in this direction, but your like it's a, let's say it's a rope, your string is in here, which means you're going to make a negative, right? Because your cos, for example, cos 120 is a negative, right? Yeah, and the work is also negative. So this is when negative work happens, because your force is somehow, preventing the motion, and so it's decreasing, less acceleration. I mean, less velocity. Is that making sense?
Yeah.
Let's do problem 2.
15 kilogram is moved along the horizontal pole by a vertical stream. Okay. 15 kilogram for 90 degree angle of the horizontal rope 30 degrees. The tension in the rope is 69 newtons. How much work is done on the crate by the worker? Distance. Okay. Work equals FD. So we just need to find the example component. Root 3 over 2. Two times 69. 69. Root 3 over 2 times 10. So
Yeah, that's it. Yeah, that's the word.
Yeah.
And the unit's J.
Yeah.
Which also you can write it N M also okay. If you write N M, that is okay. You can also write J. Same thing. The equivalent. So this is actually not only happens in real physical, there also happens in like a real kind of philosophy. Saying, are you getting any work done? So this happen in philosophy, also happening in real life, also happening in physics, right? Yeah, we use this one to describe. Of course, there's other definitions of work, but this is just the one that we use. It's good for future energy transformation. Three.
The coefficient of kinetic. Okay. The coefficient. Okay. Sure. 69 again. This time. Wait, how much did it say the crate weighs, or does it not say how much it weighs? 15 kilograms? 15 kilograms. Oh, 150. 50. And so here is 0.4. 0.4 times 150. 60. So just subtract that from last time. Oh, let's not asking for that. How much work is done by the 0?
Yeah.
Because it's not moving.
Yes.
How much work is done by friction? How much work is done by the friction? Wait. It's not really doing work because it's not going in the direction. It'd be like negative.
You're still using 10 meter.
10 meter. 60 newtons over 10 meters. The friction force subtracts the, it would
Probably have to draw more.
energy. It would take more work with friction, so that means friction does negative work, right?
Yeah, negative work. Yeah.
Negative.
Stopping that, trying to prevent it from moving.
Negative 600. Negative 600 joules.
Well, not so. Not, it's just the. I have a formula, right, for friction.
Oh, wait, why did I get 60? Oh, wait, yeah. Yeah, 0.4 times 150. 60 newtons. And if it's going -10.
Oh, wait. You probably have to rethink your friction. Are you using 0.4 times this as the friction?
Yeah.
You're assuming this is the normal force, right?
Yeah.
But I said normal force doesn't really have a formula. So you
Okay.
have to actually find what exactly happened in this like vertical direction. So you have these,
I forgot the
yeah,
vertical
yeah, there's a component
so
there, right? There's a
69 halves.
component there, right?
So it's 150 minus 69 halves.
Minus
60.
61, what? 69. Oh, that's a cosine theta.
Cosine theta.
Yeah, yeah.
Okay. So
Oh,
then
you're
that would
using a
be
special angle at that. Yeah.
34.5. 150 minus 34.5. 115.5 times 0.4 equals 46.2
Yeah,
and
that's
over 10
the
meters in.
friction.
So negative 462 joules.
Yeah.
Okay, makes sense. Makes sense.
Also, that makes sense is because, well, because and some people ask, why do we get negative? It's because the force is also negative, right? The
Mm-hmm.
friction. So I'm writing negative represent that. Actually, makes sense. That's why we
Mm-hmm.
keep that, and also it's good for conservation of energy in the future. Conservation of energy or energy thing is a big theme even in the movies, right? Like Avenger or Transformers, they always fight for energy of life. Example 4. Oh, so anyway, this still indicates normal force always stop. It's like a normal force, it's a stop line, it's a traffic light. Does that make sense? Every time.
Mm-hmm.
Well, I should say you should draw the diagram anyway, even though you think you know. But I would say at least when you see normal force, you have to stop. You have to draw it carefully. Because we don't really have. It can only done by the diagram, basically, for normal force. 4.
It's 35 kilograms. 0.3. How much work is done? Like, how do you go this way? And then you have the mg. What's 35? 350. Oh, and so that component then is 350. 37
Yep.
degrees. And then you subtract friction. And then the normal force. Normal force is cosine.
Yeah.
350 cosine. 37 degrees. Oh, and then this has to be time multiplied by 0.3.
The MG cos 30 degree, 37 degree. They don't have a distance.
Yeah, so then this is this has to be multiplied
By 0. So this is nothing in here. Does that make sense?
Wait, how is it 0?
It's because you think about this component, which is very nice, but this component does no work.
Oh, right, because it's not in the same direction.
Yeah. And also, that was because that one, some textbooks, including this one, they also say because that force, the component is perpendicular to the distance, so that's why it's 0, right? Zero distance.
So then
Zero
friction
work.
doesn't matter for
Oh, you mean is friction matter for this question? No. Only talk about gravity's work.
Okay.
Friction is friction's work, right?
Yeah.
So we don't have to use, and also
We don't need
because when we originally give it a definition for this angle kind of work, we already said it. We do not think about sine. This component, we do not think about it because they have no zero work, right? They have zero work, so we do not think about it. We only think about it f cos theta in there. So for this one, that's why you only think about this. Right?
So it's 8 times sine 350 sine.
Yeah, just time 8, that'll be cool.
Yeah.
And then let's say there is a B question. How much work is done by normal force?
850 sine of 0.
Yeah, it's also 0.
Yeah, 0.
0. Because it's perpendicular, this is also a tricky trap. Because you are perpendicular to the distance.
Work is done by friction. Negative what was that? 350 cosine 37 times 0.3. That 9
8
times negative 8.
Or you use positive 8, use friction negative. That also works. Yeah, it's probably making more sense in there.
Okay. And then total is just before minus this one.
Yes. A plus B plus C. Since B is 0, basically it's A plus C. And also you have to be careful. A is positive and C is negative. So it's kind of like subtraction, right?
A minus C.
Yeah. Okay. Not A minus, A plus C, but C is negative.
So C is negative. So, okay, yeah.
So that's why we said this is the driving force. This is the preventing force. That's why one thing is driving it, so it's positive. One thing is stopping it, it's preventing. And this work done by a variable force. Yeah. So what if the force is like this? For example, if I have energy from the engine or controlled by my own hand, so somehow the force is increasing. What will happen there?
What?
We don't really have a solution. By our definition, we don't really have a solution. We have to use something that we do it before. Just remember when we do velocity time, and we said the area of that is gonna be my distance, right?
Yeah.
Remember? And even including the curve, right? You remember this? And then I said that the reason I can prove it is because, using this one as an example, is because I can divide so many triangles and so many rectangles. Does that make sense?
Yeah.
All the rectangles is a little, like a v times little t. And so basically they are. So this is the same. Does that make sense to you?
Mm-hmm.
Of course, imagine that because it's very narrow rectangles, so I can pretend that they are real rectangles, right?
Mm-hmm.
So that's why every part is a little like a f and this tiny distance, right? And this new f, a little bit higher f, and times a little tiny distance, right? Does that make sense?
Yeah.
So now I can also use the assumption that I have. This area is the displacements. That's before. Now I can say the area represents work by adding so many rectangles together. Does that make sense a little?
Mm-hmm.
Yeah. So now we can do it. If they change the force, like this graph, so how much work is done? Do the area, basically. From 20 to 40. Do the area.
That's the I don't remember. You can divide that like a rectangle.
It's trapezium, right? You use trapezium area.
Yeah.
Oh, divide is also working.
Um, 20 times 40, and then this height from here, 40. It's also 40 by 20. Okay. So 20 times 40 is 800. 800.
Mm.
400. So it's almost 1200. 400 divided by 1200 joule.
Yeah. So just the key is still for that VT graph, which is the area, right? The area between the graph and the x-axis. I will have one question, even for the future, for example, if I said, see, let's just say if this area is 100, this area is 50. And if I ask you, what's the displacement in this VT? What do you think? I mean, this area is 100.
Displacement.
I already tell you the area is 50. It's 1 to
Yeah.
100.
Oh, 50.
Is it 50, 100 minus 50? Is that what you do?
Yeah.
Yes, you should use minus. Yeah. If they talk about the distance, then 100 plus 50, right?
Yeah.
150. Yeah, that's the key. Even there's a positive area, there's a negative area. Well, we haven't finished this chapter. Well, so the homework is redo the question that we do in the class. And you can do several questions here.
Okay.
All of them. And you can wait into a little bit. And also that, I said chapter, which chapter? Oh, it's this. Oh, we can do this and send, if you can take a graph, that'd be nice. Take a photo.
Of the
This,
okay.
yeah, especially free response for, which chapter is this? This is chapter 4. That free response is, some of the question happens in the real test again and again. And it's better that you can do step by step. You have other questions?
No.
And work definition is just it's not difficult. It's just a definition. We have to combine with the kinetic energy and the potential energy that you learned before and learn the work energy principle. You haven't learned work energy principle, right?
No.
Yeah, you can. Yeah, but also redo the question that you asked me today in this class. Those questions
Okay.
are also difficult. They definitely show up in the real test. Some of it is the real test question. Yeah. So redo that questions and do the question that we did together and do chapter 4 free response.
Okay.
Yeah, I can check or you can send it to the group.
Okay.
Yeah, that's it. Then have a good week. Actually,
you.
have a good
Thank you.
weekend. God bless you.
Thank you. You too.
Bye.